In this final week of the semester, we are going to learn some basic cosmology and understand the big picture of our universe. And this presentation is completely my own build, and I want to keep it as simple and as accessible to you. But it still does not mean it is easy to understand, so focus and pay attention. Cosmology is the study of the universe in its entirety as a whole, different from astronomy. And what does it mean to study the big empty space? But the universe itself is not only not empty, but also has its own characteristics and evolution. For example, we can question how old is the universe and how big is it? What is its evolution history and where it is heading? What is the matter energy content? To address these questions, we still have to make lots of astronomical observations, plus a lot more. We need to link these observations and understand their connections in order to build up a story of the universe. Here I give a short and revisionistic history about our view of the universe. For the longest time, people took the Ptolemy view, which is the Earth center view. Then late 1500s to 1600s came around with Copernicus and Kepler establishing the sun-centered reality. About 300 years after that, with telescopes, William Herschel observed farther to see many more stars, expanding our world into a larger but an isolated island universe, and that Harlow Shapley determined we are not at the center of the universe. Now, Hubble in the 1920s established that we are not the only so-called universe, and showed that Andromeda is a separate island universe, actually a galaxy. Furthermore, in 1929, Hubble showed that our universe is a dynamic one, and Hubble expansion became the first pillar in modern cosmology. We can argue that time in the late 1920s is the beginning of modern cosmology with Hubble expansion. Prior to 1930s, cosmology was not yet a serious science. There was not much this scientific data to make any serious discussions. Talks were more speculative, philosophical, really have some similarities with astrology in the ancient time. Now, going back to say 1,000 years ago, indeed the ancient time, talking about the universe was no more than fancy visions about the solar system and planets and the moon and so on, which is hardly cosmology by today's standard. But that was what was perceived at the time. The grasp of cosmology definitely has changed, okay? Even in the past 100 years, there were some astronomers who do not like to discuss cosmology. I even have read opinion pieces as late as the year 2000 by astronomers, ragging on cosmology. I remember I was a bit stunned. But now, cosmology has matured into a real science. I would say situation started to turn, say, around late 1980s. Our technology has made progress, made it so impressively, from larger telescopes seeing farther and more, to increasingly more powerful computers capable of doing larger scale simulations and model computations. All these contributed to many discoveries, strengthening the scientific foundation of cosmology. Here are the major ingredients of modern cosmology: dark matter, dark energy, cosmic microwave backgrounds, and the minute fluctuations we call anisotropies on the level of 1 part in 100,000, and then Hubble expansions, and then light element abundances produced in a very early stage of the universe, literally on the time scale of first 3 minutes since birth. Finally, the large-scale structures, meaning the distribution of matter in the universe as clump by gravity. We have this concept called the pillars of cosmologies, and in terms of these pillars, modern cosmology has started to add up recently. And this is shown in chronological order, starting with Hubble expansion, that's the oldest one, started in 1929. and then Big Bang nucleosynthesis, the productions of light elements in the early stages of the universe. The idea started as late as 1940s, and then moving on to the cosmic microwave background discovered in the 60s, and the large-scale structure formation that is only well established after the year 2000s, and that's why I crossed out 3, okay, if you notice in the title, and put in 4, because it is within your lifetime, for many of your students, young students, that the structural formation became a legitimate pillars, okay? It's only recently. And let's be clear about the meaning of these pillars. They are not just teaching tools, are not just fancy talks over coffee. These are the real results that any cosmological models must satisfy. And there are so many brilliant minds out there who can build just about any models, but whatever they built, the model must match the observations, and that is not easy. And of course, we currently have a best standard cosmological model, and we will discuss that. But there are also other issues to be addressed, and new models must satisfy both what is currently working plus making new predictions that can be tested. A model that fits the current one, a new model that fits the current one and does nothing else doesn't really help, okay? And so to have these new models with new prediction to give new insights is what is really difficult. Let's talk about the first pillar, an easy description of Hubble expansion, which is the expansion of the space itself, okay? Expansion of the space itself is to use a two-dimensional surface, say on a balloon, okay, and demonstrate the observational result using ladybugs like this. As the balloon expands, the ladybugs themselves not moving, staying fixed in space on the balloon, will see each other moving farther away. The distances between ladybugs increase for all ladybugs at the same time. Okay, so just look at the picture. And do not get confused. I'm using a two-dimensional surface to pretend to be this three-dimensional world. It is the best I can do as an illustration. The space above and inside the surface has no meaning. This is not a real two-dimensional object in a three-dimensional space. It is an illustration pretending this to be the three-dimensional space. In the video Runaway Universe, Filipinko used a one-dimensional string to demonstrate the same expansion idea. Now, even if you mistakenly taken this two-dimensional sphere example literally as a real surface in the three-dimensional space, you can still get the correct idea of a universal expansion, that all objects will see all other objects moving farther away in the same way. And so whether or not you understand this balloon surface and what dimension it is in, the expansion itself and how the ladybugs observe other ladybugs is the major idea you should get, that everyone sees the same thing. Repeat, the Hubble expansion is the expansion of the space itself that increases distances between all objects. The balloon example shows that there is no center of expansion. It is happening everywhere, and every object sees the same effect. Okay, this is fully consistent with the cosmological principle that there is no preferred center. Basically, every place in the universe is the same as other places. Now, moving on to the second pillar. Here, I will try to make Big Bang nucleosynthesis as simple as possible. First, let's just read the first statement. The hot beginning of the matter era must have started with simply elementary particles such as photons, proton, and neutron, but specifically in the forms of quarks, and also neutrinos, and definitely dark matter, which I put a question mark because we actually can observe it, and others, okay? Look at this chart showing the element production and abundances with respect to time, but starting as only as a few seconds after the Big Bang. You can see also the temperature scale on the bottom right here. Okay, so here is time, and here is the temperature scale at the bottom, showing cooling along with expansion. Now, we do not go earlier than a few seconds, right? The starting point is not 0 because the formation of nuclei requires the universe to be cool enough for nuclear forces to be able to bind nucleons together on the order of 10 billion degrees Kelvin. And that is about 1 second to a few seconds after the Big Bang. And let me describe just a few major trends so you get some big ideas. First, you see that protons here, okay, protons here is far greater in number than neutrons. On this log scale y-axis, the ratio is like 6 proton to 1 neutrons, and there's effectively no other elements or light particles around because early universe, very early on, really only has nucleons, okay, basic nucleons. And then you see that the light elements starts to build up as temperature cool, right? You see these light elements starts to rise. Now, the most important production is that of helium nuclei, okay, 2 protons and 2 neutrons, which is helium-4, okay, helium-4 right here. 2 protons and 2 neutrons. You can see that it will end up as the second most abundant matter later on, behind protons, okay? Now, and you can also see, just go down the list, deuterium or hydrogen-2, which is 1 proton and 1 neutron, an isotope of hydrogen. And then you see helium-3, 2 protons, but with only 1 neutron, which is an isotope of helium. And going down, and another hydrogen isotope, H3, or tritium, which is 1 proton and 2 neutrons. Of course, any isotope of hydrogen only has 1 proton, okay? And you see, going further down, and you see very small fractions of higher elements, beryllium and lithium, and so on. So as you can see, for example, beryllium is 1 part in 10 billion right here. If you just look at where it is right here, beryllium, around right here, okay? About 1 part in 10 billions, 10 to the minus 10. It is practically nothing, but it is there. In principle, they are observable, such as from very old stars, and astronomers have been measuring them. It is still important because it is a clear prediction of the BBN physics, okay? Now, neutrons, if you look at it right here, drop dramatically. And it's the one nucleon species that really dwindles. In fact, it will go to 0 because neutron is not a stable particle, especially with other particles around. In this early stage of high temperature, high collision activities, neutrons will bind with proton to form higher elements, okay? And almost all neutrons will go into production of helium nuclei, which takes 2 neutrons to bind with 2 protons. So repeat again. So watch neutron here, and then it goes down and go down and all the way to 0. And you see that helium-4 really picks up, and that's because all the neutrons are effectively going to helium-4. And you can actually do a very easy calculation. So just listen up. Let's say you have 600 protons and 100 neutrons, the 6-to-1 ratio. Let's say you take 100 of the 600 protons and bind it with the 100 available neutrons, okay? So you have 100 protons and 100 neutrons. From that, you can form 50 helium nuclei, right? Because it takes 2 protons and 2 neutrons to form 1 helium nucleus. And so what you have end up with is 500 protons left and 50 helium nuclei. And keep in mind, protons are the hydrogen nuclei. And in this simple high school calculation, you see that the number of hydrogen atoms to to the helium atoms, okay, nuclei, is 10 to 1, okay, 10 to 1. This actually matches with the observations quite well. All right. Now the overall BBN, of course, requires sophisticated calculations, but the proton to helium ratio is very easily understood, just because it takes 2 protons and 2 neutrons to make a helium nuclei. Now, certainly you can see that the proton population dips around the 200 second mark, around right here. That both of them starts to dip. Protons and neutrons will start to dwindle in population at around the same time, okay? As they are combining to form higher elements, so it's all happening at the same time. The quick summary is this: protons and neutrons will lose in number as they form higher elements in this stage of BBN, effectively until neutrons are exhausted. So roughly, we say that the BBN is done in the first 3 minutes, okay? Done in the first 3 minutes. Now let's go to number 2. Production of helium and other isotope at each temperature can be predicted. Of course, we know we can do this because we understand nuclear physics really well. And of course, these are very sophisticated calculations that we can do, but it's very straightforward. And number 3, abundances are intimately tied with the expansion and cooling because of energy and temperature. And this is very important. If expansion was faster or slower, then abundances of these light elements would be different, because the expansion rate determines how long the hot temperature stage would last for BBN, and that would affect the total production. The faster the expansion, the faster BBN would end, to result in lower abundances. For example, if the expansion was a bit slower, more time for BBN production, then helium-4 production will last longer, and we'll see a little bit more helium-4, okay? So the specific BBN fraction observed by an astronomer are very sensitive constraint to the Hubble expansion value as well. Remember, I say that any cosmological model must satisfy all observations. BBN abundances put a tight restriction on what is allowed. For example, you just cannot have a crazy model with a high expansion rate, a high Hubble expansion rate in the BBN era. It will violate the observation, and you just cannot have that. The last slide was a little bit long because BBN is very important, but here we're going to go quicker. Remember, we were studying stars, and stars make helium and other elements, right? These are not BBN helium, and helium made from stars do not come close to the helium abundance in the universe that we observed. Effectively, all the helium in the universe was produced by BBN, but BBN matches the abundances, okay? All right? And I have a recommendation. Professor Steven Weinberg was at the University of Texas at Austin when I was an undergraduate there. He passed away in 2021. He's a creator. He is a creator of the standard particle physics model that holds true till today. And the knowledge of the physics of the elementary particles profoundly contributed to the understanding of the universe, including the early stages like BBN. And so it is a very important contribution for cosmology. And by the way, he's a Nobel laureate for 1979. So here's a quick summary of the BBN: synthesis of light elements in the early stages, channels and abundances predictable by fundamental nuclear and thermal physics. Observation matched the relative abundances for a certain set of cosmological parameters, meaning that there is a very small set of cosmological models that work for matching BBN. And BBN is a strong constraint on the early conditions of the universe, meaning that any cosmological model must satisfy BBN first. We have discussed dark matter extensively, but it was already predicted and observed in 1930s. And it's not until the 1970s, Vera Rubin, with careful measurements of galactic rotational curve, established the missing mass firmly. And by the way, this is a Newtonian gravity analysis. The modern way is through gravitational lensing, the distortion of astronomical images by foreground mass as according to Einstein's description of gravity. So both ways, using the formulations of two geniuses, lead to the same conclusion of dark matter. And there are other ways to show dark matter. And for example, our analysis of the cosmic microwave background clearly points to dark matter affecting the statistical pattern that we observe. In other words, if there's no dark matter, CMB will appear differently. And also, galactic structure and simulations describing the cosmic web of matter distribution also need dark matter, or else the result will look different. So the impact of dark matter is a key component affecting the evolution and the characteristics of the universe. So now you can see that every component affects the others. They all must be self-consistent together. And that's why having a good cosmological model is a huge achievement. And you cannot get away from any one particular set of observations, facts, or established theories. You must satisfy all of them simultaneously. Now, this slide is for fun and also to make a human connection. Vera Rubin taught at the local Montgomery College, specifically in the Silver Spring branch for 1 year, and I forgot what year that was. And she was later then at the Department of Terrestrial Magnetism here in DC, and she passed away on Christmas 2018. And she's quite famous now, even though in her younger time she was not getting the credit she deserved. And the latest one, the LSST, a very large telescope, was renamed to Vera C. Rubin Observatory. And the latest one is NVIDIA, the huge company, currently in 2026, the largest company in the world. And right now, the leading maker of AI chips has just named the latest chip, the Rubin chip, or the Rubin platform. It is named after her. And here is a very unique historical artifact that I own, and it dates all the way back to the ancient era of, I think, 2007. It is a pen bearing logo of Large Synoptic Survey Telescope, LSST, touted as going wide, fast, and deep. And of course, it is now the Vera C. Rubin Observatory. Okay, by the way, this slide is just for fun. This is a partial list on the background on the history of the work on CMB, and we do not need to read all of it. All these folks are very famous astronomers, physicists, and astrophysicists, and it started as early as 1940s, and folks continue to work on it. And this is just a very small sample, okay? If you're interested, you can really read a lot about the history of this thing. But the most important one, arguably, is the detection of the CMB hissing by Penzias and Wilson in 1964. In terms of CMB detection and measurements, let's explain it in four generations. The 0th generation, the accidental discovery, is of course by Penzias and Wilson, was the AT&T Bell Labs radio horn from the ground in Homedale, New Jersey, okay? Now, the first generation of space measurement is COBE, the Cosmic Background Explorer, short as COBE. It is an all-sky survey. And we will talk more about COBE because this is the trailblazer setting up all future generations. And we also see in the picture the central band of red from the all-sky survey. That is the galactic emission of our Milky Way galaxy. Remember, we are in the disk, so we cannot see through the disk. But the galactic emissions, although a nuisance interfering with CMB observations, they are very useful for various astronomy research on our own galaxy, okay? Now, the second generation is the Wilkinson Anisotropy Probe, or WMAP for short. It is far away, okay, at a place called Lagrangian point 2. Only the most serious and mature projects will be sent there. And there it provides quality and precise data to allow the first study of the evolutionary history, seriously improving upon the first generation COBE. Okay, this is the first time we came to know the big picture of the universe's history as backed up by data. Before this, the understanding was more or less patchy work. And the third generation, which is going on right now, is the Planck surveyor, also a Lagrangian point 2, going to very high precision cosmology. And by the way, the third generation, but Planck surveyor, is by ESA, the European Space Agency, and the first two generation, COBE and WMAP, were by NASA. COBE has three instruments. One of them is FIRAS, made to detect the spectrum of CMB, and FIRA stands for Far Infrared Absolute Spectrometers. And the spectrum is the energy distribution with respect to wavelengths of frequency. And the stunning result from FIRA is data and theoretical curve, meaning the Planck distribution of ideal thermal emission spectrum. They agree to 0.005%, or 5 parts in 100,000. That is how amazingly agreeable they are, okay? And you can look at the the picture below, the plot below. What it shows is a 2.73 background temperature, Kelvin, 2.73 Kelvin. And it is it is effectively a perfect blackbody thermal emission spectrum, showing that the early universe was in nearly perfect thermal equilibrium under very clean and ideal conditions, okay? It is the most perfect blackbody spectrum produced by nature as far as we know, as far as we have measured in anything, all right? Now, except for the very small imperfection, what we call anisotropies, and that is to be measured by the second instrument, DMR, and show the all-sky imperfection on the level of 1 part in 100,000, which is 0.001%. And we will discuss that next. Well, COBE FIRAS deliver the stunning result of a perfect blackbody spectrum of the CMB. However, we expect still the small anisotropies or imperfection or small fluctuation in the otherwise perfectly background, okay? And COBE DMR actually measure that. But here, we're going to show you the result from all three generations, COBE, WMAP, and Planck, showing the all-sky map survey show these small anisotropies, these small variation in the temperature map, okay? And you can see that COBE is a little bit blurry in comparison, but you can still see the variation. WMAP is certainly much more improved, and Planck took it to a much higher precision, showing the much greater details of these variations. We are not showing the COBE map, but the Planck CMB map, processed and cleaned up, showing hot and cold spots. But COBE certainly show these anisotropies already, but here we are showing the Planck result for greater clarity. If you're like an engineer, like studying noise, such as in communication, you may immediately recognize there are some patterns to this. This is not a random noise map. We had anticipated some patterns, and this map is not just a pretty map confirming CMB existence. We can do mathematical and model analyses to figure out lots of information about the universe. Remember, CMB photons are from more than 13 billion years ago, and conditions of the universe affected these photons. And so CMB photons contain information, historical evidence of the universe. And we can extract these information provided we have some good models. and of course based on good physical principles, from which we can do good analyses. Okay. Now I want to point out that CMB dataset is a huge cosmological dataset, and it alone effectively reveals the universe's secret. Okay, we can certainly combine it with other cosmological dataset, but CMB dataset so far is the dominant one. The mathematical way to understand the all-sky CMB temperature map, and I mean for studying and analyzing cosmological data, is to transform it into a so-called correlation power spectrum. This is still data processing, not yet physical analysis. Okay, this is take the CMB data map that you see from the previous slide, and then translate it into this mathematical representation. And right here, this is the Planck representation, and here this is WMAP plus other surveys, okay, other balloon surveys, combine them together. Long story short, each correlation number in the plot represents how correlated different spots are with one another at any particular angular separation scale. For example, we can examine these correlation at 1 degree apart, 2 degrees apart, and so on, and quantify the correlation. You may not understand it, but I will explain it soon. Now, I will point out just two features. One is that the mathematical pattern that you see is definitely not random. Just look at it. It doesn't look random, right? It looks very mathematical. Anyone with a scientific or mathematical mind will immediately wonder what processes can generate these patterns in the CMB. Now, the second one is to look at the 1 degree result. For Planck is right here, 1 degree, and for WMAP is right here. All right. What we see here is we see a peak value in the correlation around 1 degree. What this means is the following. Okay, it's a physical explanation. You look at any spot in the map, say hot spot. Okay, it doesn't matter. Just pick any spot. If you look at other spots 1 degree away from the first spot that you pick, you are also likely to see a hot spot. And that's what high correlation means. It means that, at this angular separation apart, you are likely to see them correlated. And the strongest correlation is at the 1 degree scale. Okay, so this is definitely some information that tells you about something happening on this cosmological scale of 1 degree separation. Okay, and we also see other interesting features. Other interesting features like the second and third peak at smaller angular scale. Now, we have not translated this mathematical fact into physical results yet, and that would require having some physical models to do analyses. Even before we start deep diving into the physics, okay, we can already start asking some very good questions just from the observations. What is the observational result telling us? Okay, so number one, for example, why would CMB from the opposite ends of the universe be identical? There's no reason for them to be identical at all. What caused two opposite ends of the universe supposedly did not know anything about one another to have the same results, okay? And in fact, all cosmological data, not just CMB, present this puzzle. How can the entire universe be so uniformly the same as if they had been in communication with one another, okay? Similar question like this, even before CMB, led to another grand idea called inflation, and we will discuss that later, okay? And the second one, for example, what created the correlation structure at different spatial scales, right? And there's really a lot more questions that we can ask, and these are just directly from observation. We don't even need physics to address these questions. The observations tell you something really strange. I want to enhance the understanding a little bit better, but I will just read off this slide. Cosmology has not always been a rigorous science, and some astronomers show disdain even after COBE and CMB. History of cosmology is replete with pseudoscience and philosophical discussions. There were some similarities to astrology, okay? But current cosmology has several major data sets to make it a real science. And when you think about the history of astronomy or even many sciences, this is not surprising. If you don't have data, what can you do? Okay? And so the progress of theories and physical laws during the entire 20th century, such as particle physics, is also necessary. You need data and you need theories. Okay? They go hand in hand. And more interesting points. And the most important one is probably that Hubble expansion can be superluminal, meaning greater than the speed of light. And many are confused by this, and how can anything moves faster than the speed of light? And this is where you need someone like me to tell you the proper context. The statement about nothing moves faster than the speed of light is referring to any object moving in space. But Hubble expansion is the space itself. So it is outside the physics context of that statement, okay? So Hubble expansion is about the the expansion of the space itself, okay? And that's why it has no restriction limited by the speed of light as statement, okay? Make sure you understand that. Now, the second one is helium is 25% of the universe by mass, probably about 10% by number. And helium is almost all primordial, generated in the early stages of the universe, okay? And next point, CMB photons permeate the universe around 400 per centimeter cube, a medium-sized home fish tank. Okay, think of a fish tank. There's about 400 million CMB photons at any time contained in that, okay, going through that, okay? Now, here's another one. Many of you youngsters may not know what a tube TV is, but just keep in mind that digital TVs are basically only true in the past decades or 2 decades ago, all right? Now, an old tube TV's hissing when we turn on the TV and there's no programs on, okay, and because TV programs were not on 24 hours a day, and you will see these white noise on the screen, these grays and black and white noise on the screen, and some of that is partly CMB photons being caught by TV's antenna, and that's an interesting fact for you to enjoy. The CMB hot era, loosely stated, is where CMB photons establish their characteristics before being sent out. And this era is, of course, after BBN. This period is roughly the first few minutes to the decoupling era, about 300 to 700,000 years after the Big Bang. And photons, electrons, and nucleons were in this period in nearly perfect thermal and collisional equilibriums and interactions. And we call this baryon photon acoustic oscillations, meaning matter and photons were hitting one another, establishing a regular interaction pattern of pushing each other. In particular, nucleons move back and forth in a consistent way. And the model describing this is straightforward and works out beautifully. It is actually a very important part of the cosmological model to have this very straightforward interaction built into the standard cosmology. Otherwise, we will not get it right, okay? And different regions have very slightly different mass and gravitational variations, slightly hotter or colder. This is an imprint of the earlier quantum fluctuations and the local gravitational environment for the CMB photons, resulting in CMB anisotropies. So different regions are almost identical except for these tiny differences due to mass and gravitational variation, supposedly from quantum beginnings. and will result in slightly different CMB photon temperatures that we can measure today. Okay, and then going on, matters and photons in the entire universe were undergoing oscillation in each own local regions. And these physical scales of interactions leave behind detectable clues in the galaxy distribution as well, not just in CMB. All right. Now, dark matter, of course, not being very interactive, not affected by photons as much, have really began to clump. Okay. At this point, regular matters like nucleon cannot clump yet because it's being interfered by photon. But dark matter is much more free, and they have already begun to clump due to gravities. Okay, but at this point, CMB photons are very hot in the high gamma ray range, from billions of degrees, but slowly down to hundreds of thousands in this period as the universe continues to expand and cool. I repeat, the hot matter era was the period where CMB photons established their characteristics, especially the temperature, the regional variations, and the different physical scales naturally coming out of these interactions. That photons and nucleons were constantly hitting one another. But at some point, as the universe cooled enough, okay, whatever they were doing will come to a stop. And so let's read the first statement. CMB were the photons from the particularly early recombination era, when the universe cooled due to expansion to about 4,000 Kelvin. Electrons and protons were able to combine to form hydrogen atoms, no longer being interfered with by photon. Consequently, the universe was becoming free of charged particles, and also photons began to travel freely. And you will hear names such as recombination, decoupling, last scattering. Now, recombination refers to electrons and protons combined to form hydrogen atoms. Decoupling refers to photons and matter becoming free of one another, no longer in constant collision. Last scattering refers to photon finally scatter off a proton for the last time and became free to travel through, ending up in a long, long journey across the universe. And so these different names simply describe different aspects of the same event. And this process began around 300,000 years after the Big Bang. Some will be more specific to say 380,000, okay? And nevertheless, the process continued on for many more hundreds of thousands of years. But nevertheless, this period of about 300,000 years, if we translate that to a human life scale, it's like a one-day baby in a human life of 100 years. That's how young it was. Now, the decoupling goes both ways. Atoms and photons broke free of one another. They are no longer interfering with one another. And this is where what we call the free streaming of photons began at this era, meaning that the CMB photon can finally now travel without much interference. And this is where why we can observe CMB photons at this present stage. This illustration shows last scattering quite okay. In the green, when the universe was still quite hot, protons and photons are interacting. Here, red represents protons and aqua color represents electrons, okay? But when the universe became cooled enough in the yellow part, hydrogen atoms form, and you can see is aqua color dot around a central red dot, okay? And now photons can free stream, meaning no collision with matter, and will begin to travel on freely. And what is the last scattering surface? CMB photons are and were everywhere. When the last scattering era began, CMB photons everywhere began to free stream in all directions, okay? CMB photons everywhere began to stream freely in all directions. But the CMB photons we are observing today must have originated from a particular spherical surface that happened to travel in our direction. So we are just observing a very small sample of the entire CMB photons in the universe, specifically from a spherical surface long time ago. A different observer in a different part of the universe will observe her own the last scattering surface. Okay, so our last scattering surface is the boundary of the visible universe, of course, because these are the photons that have traveled the entire distance at the speed of light. It cannot be more than this. Okay, now finally, the universe has since expanded to a much larger extent. Whatever that surface is no longer at that place. Okay, that place has now expanded to a much greater to a greater distance. And specifically, I will just give you a preview that he has expanded 1,000 times farther away. Beyond confirming the CMB existence, there is one connection of the CMB to the present time we must have. The CMB must necessarily connect to galaxy distribution of today. So let's read here. Matter-photon interaction not only determines scales of the CMB, but also in a matter distribution that will lead to galaxy formation. The matter structure formation since the recombination era, or last scattering, or decoupling, must result in a galaxy pattern we see today. Because CMB was in equilibrium with baryon matter, the CMB temperature map is also a proxy map of the matter distribution, with tiny variations built in. These variations, over time via gravity, grew into the large-scale matter structure in the present time. So a successful cosmological model must match the current observations, but also link it directly to CMB anisotropies. And we do see that. This was discussed in the previous two lectures. Powerful computer simulation show the result fully consistent with today's large-scale structure. Let's talk about the journey of the CMB photons. CMB began its 13 billion years of journey after decoupling from matter, and they were and are everywhere, streaming in all directions. These photons have been redshifting since because of the expansion of the universe, cooling along with it from very hot, high frequency, to now very cold, low frequency. Now, while CMB photons were traveling, ordinary matter was doing its own things. Gravity was pulling them together. Eventually, the first galaxies and stars were formed. And this is the reionization era, when the universe begins to light up. And that's because the stars were beginning to shine. This is known as the first light of the universe, roughly 400 million to about 1 billion years after the Big Bang. And of course, before the CMB and the first light, there were no stars, no galaxies. And so we refer to this loosely as the Dark Ages. And because of reionization, basically the first stars and galaxies were born, this will put some dents in the CMB patterns because of some interference, some additional interactions, but not too badly, but it's something we can calculate. And also in the last few billion years or so, this is the last bullet, dark energy started to appear and started to impact the expansion of the universe, thus further affecting the wavelengths or energy of CMB photons. And there are many more. So CMB dataset is very rich, containing lots of information from many cosmological events, each impacting CMB photons differently. These information can be extracted from the CMB dataset using good models. CMB data tells a very compelling story about the universe. The universe at the age of about 300,000 years, shown by the CMB, is very simple and uniform. And there's almost no possibility of any processes happen in a way different than what we know now. And we are quite sure that the Big Bang happened the way we think it did, at least down to a very small fraction of a second, like 10 to the minus 43, so-called Planck time. There are always challengers to the standard understanding, but so far, our standard understanding is pretty much really solid, okay? And so, early universe was almost featureless, but with minute fluctuation we call anisotropies are the smoking gun evidence of even earlier time, like the quantum beginning, because we believe that quantum physics predicts a universe's beginning that is not perfectly uniform just due to quantum physics principle, with variations that arose from quantum fluctuation. And we believe CMB shows exactly that, okay? And structures we observe today have developed from a tiny deviation shown in the CMB imprints and the anisotropies, and CMB statistics can be shown to be fully consistent with galaxy distribution statistics we shown today. If the universe was 100% uniform, then the large-scale structure we see today would not exist, or it would look very different. Okay, the 1 in the 10 to the minus 5 deviations, 1 in 100,000 deviations in the CMB map were very small, but enough for gravity to act on these tiny imbalances and started to clump matter together towards the slightly denser regions and form the large-scale structure we know today. And so the CMB itself not only shows what happened many, many years ago, we're talking about 13 billion years ago, but we can also connect that to the very present time, a direct descendants of that time, right? The galaxy distribution, the way that it looked is a direct result of what happened at the time because of gravity. Now, number 3, and there are many other details such as the 3 neutrino species as predicted by the standard particle model, all right? And this, for example, the standard particle physics model includes 3 neutrino species, or we call generations. And people have tried to use 4 as a test ground, 4 neutrino species in simulation, and that just will not work out. And so there were so many tests being done, it just has to be 3 neutrino species. It cannot even be 3.1 or some crazy number like 2.9. It just has to be 3. Now, so the CMB data set amazed us for many years, because as we do more tests and simulations and add on other real observations, as we continue to make progress, we became more and more confident that CMB is telling us a very consistent story. In fact, the entire cosmological data from everything together, they tell us a very good story. Now, we will summarize that at the end. Now, imagine in real life a crime scene and 100 witnesses and all evidence point to the same thing. That's how amazing this is, okay? So everything we know is consistent with one another in terms of our overall cosmological understanding. Cosmological data, astronomical observation, physical principles, specific physical parameters, and so on, establish a very tight model about the evolution of the universe. Now I will talk about a topic that may be more abstract, but is nevertheless revealed by the CMB data. We were able to extract, for the first time, the information about the geometry of the universe. But what does that mean? Perhaps an easy example is to refer back to black holes. We know that space-time around a black hole is curved. One way you would know that is that you cannot apply Euclidean geometry. And one easy Euclidean geometry test is Pythagorean theorem of a right triangle. Try to draw a right triangle around a black hole, and you will see that a square plus b square equals c square will not work. I've also said you can draw a right triangle on a basketball, and then it will not work as well because the surface of the basketball is curved. So you don't even need to imagine a black hole. Okay, you can use the surface of a basketball to understand that it will not work out for Pythagorean theorem or any Euclidean geometry. So in any weird situation, whether it is the curvature of a space-time or a physical curvature of the surface of a basketball, Pythagorean theorem will not work. Now, for this information, Kobe CMB is not refined enough for this information, cannot reveal the geometry of the universe. However, WMAP CMB right here is good enough and reveals that the geometry of the universe is flat. It means Euclidean geometry with no or very small space curvature. Okay? Now, that the universe is, by and large, is a flat universe. Oh, by the way, the word flat is deceptive. It simply means space has no curvature. Not that the universe is flat like a sheet. Okay, that's not what we're talking about here. But it is flat in the sense of we can use Euclidean geometry like Pythagorean theorem. Draw a right triangle in the universe, and you can apply a squared plus b squared equals c squared. This illustration that you're seeing right now shows that the CMB map will look different for different geometries of the universe. And because different curvatures affect the appearance of the CMB map differently. That's why we know we have a flat geometry. By the way, different geometries would affect not just CMB, but all cosmological data as well as many larger astronomical data sets. In the future, say for example, when we have more galaxy data, maybe the galaxy structure can also reveal a flat universe. Well, it has to. We expect nothing different because the curvature of the universe affects everything as a whole. Now, in addition, in the case of open or closed geometry of the universe, of course, Pythagorean theorem will not work anywhere. Okay? And however, whatever this is, the idea of a flat geometry lends support to inflation, another fantastical idea. Okay, but we will discuss that very soon. But before that, let's discuss the flat universe a bit more. The universe has many black holes, some supermassive, creating curved space here and there. And that is true, even just around any massive object like a star or even around Earth. The space will be curved a bit by the presence of mass, okay? So, there are these tiny curvatures, regional curvatures here and there, okay? But in comparison with this huge universe, okay, this huge universe is mostly of empty space. And the curvature by the presence of mass is effectively nothing, okay? Very, very, very tiny to affect the curvature of the universe as a whole, okay? And CMB photons measured by us mostly are not impacted by the presence of these local curvatures, okay? Not at all. And so the flat geometry of the universe is a huge result revealed by the CMB. Okay, it's been almost an hour, so let's take an intermission. Okay, I pretend that you have just taken a long intermission, and we are going to continue with the remaining part. This slide is about the fantastical idea of inflation. The idea of inflation existed before 1980s when physicists and cosmologists were already thinking about the characteristics of the universe. The story is a bit complicated, and I will not go through it here. The rough idea is that the universe, at the very early beginning, went through a period of incredible expansion, but it is not the same as Hubble expansion. So be careful here. It is not the same as Hubble expansion. This inflation has to be very early on, maybe say in the Planck time, very early on. We do not know. But so many puzzles existing in physics, astronomy, and cosmologies can be explained away by inflation. And one puzzle is the communication puzzle. Why do opposite ends of the universe appear identical as if they were in contact and resulted in the same condition? Well, inflation says that the entire universe early on was in communication as a much smaller entity, and therefore established equilibrium very early on. Then inflation occurred, stretching out the universe to an incredibly large size, but the conditions had already been set. Okay, and that's why you see the same condition across the universe. The other is the flatness, the flat geometry of the universe. Why is the universe flat? For example, suppose the universe was born of any curved geometry and was not flat, but with inflation, stretching out the distance scale to very, very large distances, okay? When any object is stretched out this much, any curvature or any wrinkles are stretched out to appear pretty flat, okay? It's not a bad idea. It is much better than other fantastical models that just happen to create the universe with exactly zero curvatures, okay? We do not like models that does not provide explanation, but rather than just say, oh, here it is, that's just the way it is. We just do not like that. The reality problem, of course, is that we do not have direct observational data on inflation. We just don't have the data. We have to rely on strong inferences from the subsequent results, okay? And how much was this inflation? How strong was it? We are talking about like stretching 1 meter to 1 to the 30th power, okay? 1 meter to 1 to the 30th power. It's like taking a meter stick and stretch it to 1 billion meters long and more. This is a serious expansion. That's how crazy it is. And yet, it seems a good idea to explain all these puzzles. All right? And to continue on even more fantastical ideas, around year 2000s, the study of inflation led to even more of a crazy idea called the multiverse, but it's a very natural consequence of theories based on quantum physics. And let me just take one minute to reflect on how amazing this is. When quantum physics started in early 1900s, its strange behavior shocked the world. I'm sure you heard of Schrodinger's cat, that a quantum cat can be both alive and dead simultaneously. It is actually a thought experiment. It is an illustration to explain the Copenhagen interpretation of quantum physics. It's a way to understand quantum physics in an operational, practical matter, collectively called the measurement theory. Okay, so however you want to call it, you can think of it as a Copenhagen interpretation. Now, there are many technical details, but I will go to the crux of this issue, that many people do not find this interpretation completely satisfactory, and there are other competing interpretation, some other ideas to explain quantum mechanics. One of such interpretations, considered better by many, is the many world interpretation of quantum physics. The many world interpretation. But people were certainly not imagining different physical worlds popping out at every stage of the quantum world evolution. Okay? That's really not what people were thinking about. Okay? But recently, Professor Andre Linde of Stanford University, working with inflation. By the way, he is one of the Papa physics in terms of creating inflation model, okay? He thoroughly connected the initial quantum states of the universe to inflation and something new, the multiverse. All of a sudden, the many world interpretation seems more than just a way to understand quantum physics, but can actually be a real description of the physical world. The connection, it is still not yet clear, but when you have many world interpretation and then you have the multiverse together and they are both quantum physics, your mind really start racing, okay? Now, the multiverse idea is still developing, so I will not take these presentation too far in this course, but nevertheless, fantastic models exist, and I must say, it is looking pretty good. I mean, first it looks crazy, but it's been 20 years and more. It is looking more and more solid. And so, man, here we go again. Can this crazy idea be for real? CMB data is very rich, and on the other hand, because of how rich it is, it provided many constraints for the cosmological models. First, the most important one is that it has to be flat Euclidean geometry. The universe is not a curved space, and it's definitely sets a result for cold dark matter model and structural growth, meaning that dark matter was not hot, okay? This is very important, and definitely provides a strong clue to dark energy even before the supernova hunters were finding out the fantastical result. CMB had revealed the presence of dark energy, and there's so much information embedded within the CMB that we essentially had grasped onto the story of the universe of the past 13 billion years. Finally, we will discuss the granddaddy of all current mysteries, dark energy. But let's clarify the followings. We observe the acceleration of the universe's expansion using type 1a supernovae as standard candles. Whatever factor causing the acceleration, we just call it dark energy. Basically means we have no idea. We are ignorant. We just call it dark energy. Okay? We do not know what it is. Not surprisingly, the smartest theorists, they scramble, try to come up with numerous theories and models to connect dark energy to something real. But here I'm going to present you the most interesting stories going back to early 1900s when Einstein was working with his general relativity. The official historical account is that Einstein introduced and published his equation in 1915. We're talking about general relativity here, not special relativity. Okay, but certainly he had been working on it for years prior. And the equation that you are looking at is known as the Einstein's field equation. Einstein's field equation. It is a description of gravity, and you are looking at it, looking quite simple. Oh, by the way, the original introduction is without a third term, the cosmological constant. And so the original introduction, you have to ignore the third term, the cosmological constant. We're going to come back to talk about it later. The key point is that gravity is an attractive force. When the formulation is applied to the universe, the result shows that a shrinking universe, okay? The result shows a shrinking universe because gravitational effect pulls the universe tighter and tighter. Actually, that's quite straightforward and obvious. Now, keep in mind, this is around 1915. People did not have the observations or the insights we have today. If you remember, around this time, people were still in belief of the Long Island universe by William Herschel, without even knowing for certain that Andromeda Nebula was actually a distant galaxy. And that's how people were in the dark about our galactic surrounding, about this entire universe. Einstein, like many folks, had a view of a fixed, steady, and beautiful universe. However, his equations pointed towards a dynamically shrinking universe. Well, that's not what he wanted, okay? So in order to achieve the result of a non-moving universe, a steady universe, Einstein made a very interesting move. In 1917, he introduced a constant term into the equation, and that's what we're talking about right here, that operates as a countering force. This term is called the cosmological constant. Now, I'm not going to explain the mathematical nature of the equation or the cosmological constant. I would just say that Einstein's he he understood the mathematical nature of the equation so well that he knew a constant term is permissible within the framework without changing the nature of the description. Okay? The cosmological constant acts like a repulsive force, countering gravity, and with the right value will achieve the delicate balance needed to have a steady, non-moving universe. So cosmological constant will counter gravity and balances out, so there's no motion, there's no movement. And he actually did calculate it. He calculated a value of the cosmological constant for the steady universe he wanted. Okay, so there was actually a value he calculated. Now, personally, I thought that was brilliant. The genius made one brilliant move after another. Okay, regardless that he was wrong. Okay, it was still brilliant. The problem was, of course, in 1929. Okay, 1929 came along with the announcement of Hubble's expansion. Okay, shattering the view of a constant universe. Okay, now Einstein called this his greatest blunder for not seeing the possibility of a dynamic universe. He wanted a constant universe, but his equation says there is no constant universe. The field equation itself actually, does not prevent expansion, just that gravity is attractive and will slow down the expansion. And there was no need for cosmological constant in the first place. If there was a Big Bang, universe came out with an expansion, you just need to work out gravity to say how much does it slow down. That's all. There was no need for cosmological constant. The equation in all the description is perfectly fine. And since then, cosmological constant faded into obscurity, not discussed for almost the next century. I myself, throughout all my learning, all the way to graduate school, has never been taught about the cosmological constant in any course. I never heard it mentioned, not even once. Okay, and that was in my time. Okay, well, so was the cosmological constant really a blunder? Well, the famous personality that we know, Neil deGrasse Tyson, in his remake of the famous TV series Cosmos, which aired in 2014, in episode 1 he said, I'm going to talk about a man who was so smart that even when he was wrong, well, he was right. And of course, he was talking about Einstein. Okay, Neil deGrasse Tyson was talking about Einstein. With the recent discovery of the acceleration of the universe in late 1990s, I'll say maybe 1998 when officially announced, the cosmological constant resurrected because it provides a very straightforward explanation that is really allowed inside the Einstein's equation. There is no need to turn Einstein's theory, right? There's no need to turn Einstein's theory upside down or change it dramatically. It has always been there. We just have to accept the existence of a cosmological constant whose value is large enough to match current observation. That's all. It has always been there. There's nothing new. We just need to dig it out and put it back. Now, let's have a fun and short fun discussion. I can say that Einstein made not one blunder, but two great blunders, okay? Two. Not only he did not foresee a dynamic universe, and that's why he included the cosmological constant. But once the cosmological constant was included, he could have easily seen the possibility of an accelerating universe, okay? So he missed both times, okay? But that's not going to take away his genius, all right? Everyone's human. Now, and in the current time, the cosmological constant is a nightmare for theorists, okay? It really bothers them. There's literally nothing you can do with this term other than to just accept it, okay? It is a constant. There is no physical explanation for it. There is no dynamic to it other than being a constant pushing pushing the universe that's always going to be present. And yet, cosmological constant leads to the greatest and the most dreadful ending of the universe, ending in a big freeze. And I like to call it the big nothing. Okay, and that's it. All right. So theorists madly scramble to come up with actual physical model, try to replace the cosmological constant, and that effort continues. So far, you can't say anyone has succeeded. We just do not know what is dark energy. You can say cosmological constant is a model, but everything is a model. Right now, there's nothing that's better than anything else. Okay, so the quick summary is this. Einstein introduced the cosmological constant to explain a steady universe, but that was abandoned after the discovery of Hubble expansion. But in 1998 or so, when supernova hunters discovered the acceleration of the universe, the cosmological constant came back strong as a candidate to explain the effect of dark energy. And its advantage is it is already in the Einstein's field equation. There is no need for anyone to come up with any new theories. But the problem is theorists do not like it because, as we said, okay, we do not want a theory that just say it is just there and there's nothing more. We don't like this kind of a theory, and most theorists just cannot accept it. So here in the title, I started out with standard lore, okay? Because before, cosmology was just a standard story. But now I crossed out lore and put in model. Now cosmology has finally become a real science, and the standard cosmological model continues to strengthen, and this is what we understand as of now. The quantum mechanical beginning set the seeds of gravitational fluctuation and anomalies, which we later observed as the CMB anisotropies. In a very early stage, inflation quickly expanded the universe, curved or not, to a nearly flat geometry, resulting also in same conditions across the universe. And of course, the universe continued to go through particle reductions all the way up to the BBN, leading up to the hot matter era. Okay, the hot matter era was in thermal equilibrium, where photons and matter interacted, and this is where CMB establishes characteristics and later on originate. Okay, along the same time, structure growth had already begun with dark matter, which was cold and did not interact with photons. So even in the hot matter era, dark matter could start clumping due to gravity. But of course, when CMB and matter decoupling occurred, the baryon or the visible matter also began to clump due to gravity. Right now, photons and matter, visible matter, are now free of one another. So this is when matter and dark matter together were both interacting and clumping by gravity, okay? And of course, Hubble expansion is the slow expansion afterward for the rest of the universe time. And recently, dark energy reared its head after about 7 to 9 billion years. So dark energy did not always exist or impacted the expansion of the universe. It had only become strong enough, with its magnitude large enough for the acceleration value to become sort of observable. So here is a fuller illustration of the timeline of the universe, specifically showing the Planck era in the very, very beginning, right here. Okay, just showing you right here, which is labeled as physics unknown. And we believe this is where quantum gravity theory is needed. But we do not have a successful one yet, and we cannot apply anything that we know. So this remains sort of a little bit a speculative era right here. And of course, followed by a short period of inflationary expansion. It's also kind of a speculative, but it is a strong guess because of what it can do to explain what we observe. And then we become more confident of the subsequent era, the particle physics era, quarks, subatomic particles, BBN, and so on, up to the first 3 minutes mark right here. Okay, remember we have said up to the first 3 minutes, basically all the light elements in the universe were really synthesized. And then hot matter and photon dominated for the next 300,000 years or so, maybe 400,000, until decoupling, when CMB photons started to free stream and matter began clumping via gravity, further on forming galaxy, stars, and large-scale structure until today. This illustration is a story of the universe as made by the WMAP team. I worked for the WMAP team as a postdoc researcher at NASA many years ago. The guy who made this picture specialized in graphic, and I've forgotten his name. And here I will explain some features. Okay, so we start out with a very shiny beginning, literally the very Big Bang beginning started out with a very energetic, presumably so that the quantum fluctuation beginning, and you see a very rapid extension, what we call inflation, expanded the universe to a huge extent, illustrated as a sharp widening at the beginning. The universe then went through a period where particles were produced. It's not shown here, which we'll discuss many times now. And until the CMB era, that's right here. So it says right here, after a glow lights pattern, 380,000 years afterward. Okay, after this, the CMB started to free stream and matter can begin to clump. By the way, we did not mention dark ages yet. Right here, dark ages. Well, not much. What we mean is that there were no galaxies or stars between the CMB and the first light. Okay, while there were plenty of hot CMB photons, the universe was certainly not dark in that sense with all the CMB photons. But the larger objects have not yet formed. We're talking about galaxies and stars until about 400 years later, when first stars formed and began to shine. Okay, so we like to think in terms of stars and galaxy and the shining of them. Okay, so that is when the first stars and galaxy lit up. And so we call that first light. And so we like to think between CMB and the formation of the first generation of stars and galaxy, that period, we like to call it dark ages. But in reality, there were a lot of photons, okay, CMB photons, okay? And so when the first stars began to shine, and that is referred to as the first light, okay? And about 400 million years afterward. And the Hubble expansion continued on for the next 13.7 billion years. And you can see the cone widening, okay? Because of the expansion, the space scale is expanding. The structure inside the cone, as you can see, if you look carefully, the objects becomes clumpier with time. And then you see bigger and bigger galaxy emerge because of merger, right? That's the growth of structure. For example, this galaxy here is huge, and then you see other large galaxy. You don't see them in the beginning. Now, dark energy appeared about 6 to 7 billion years ago, or at least the effect of dark energy strengthened around that time, enough so that it's beginning to affect the acceleration of the universe. In this illustration, if you pay attention, the acceleration is represented by the greater curving and the widening in the final 1/3 of the cone. So pay attention to this part. You see how this part curved up like that, okay? So this represents the acceleration of the universe, greatly accelerating the expanding spatial scale of the universe, okay? And finally, you see the WMAP spacecraft is waiting there, ready to take the data and unravel the secret of the universe. Okay, right there, that's WMAP. As of now, the universe is about 1,000 times larger than it was at the time of the CMB. And we have never really explained what redshift Z means. It is literally a measure of the expansion scale when we're talking about the cosmological redshift, okay? The redshift of the CMB is about 1,000. Okay, so in this case, what this means is this the value, the current spatial size compared to the time of CMB has expanded 1,000 times. And so in terms of cosmological redshift, that value of Z, whenever we see the early galaxy with a Z of 2 or 0.3 or whatever, it actually tells you the size of the universe now compared to then. Okay, so that is a little technical information that is often not taught. This illustration is from the Planck surveyor team. Basically the same story. But here you see both W map right here and also the Planck surveyor at the end. They added both right here. Now, I do want to point out that our understanding of the first stars and first galaxies are being refined as of now. While this illustration states the first galaxy to be about 1 billion years after the Big Bang, James Webb Space Telescope have recently observed numerous very early galaxies, 300 to 400 million years after the Big Bang, pushing the formation time much earlier than previously believed, as early as the first generation of stars, okay? So see, our cosmological understanding continue to improve. This is not going to change the big picture much at all, because these are the details in the formation processes, okay? But we do have to address those as we know more. In addition, these first galaxies and first stars are exactly what James Webb is designed for, okay, to be able to see them in an infrared. That is also something that is not well known, okay? It's not something that is said to the public. But James Webb was very much set to have his prime goal, okay, one of the prime goal, perhaps the top goal, to see the first light, the first galaxy and first stars, okay? But in any case, future illustration and future data will have to update this information about the time frame of the earliest galaxies. Okay, so we are going to finalize all this with real models. When we put all the cosmological data together, we arrived at a very strong concordance model that pinpoints an agreement on cosmological reality, specifically by only 6 parameters. This model incorporates all physical laws and processes that we know, all observational data, including CMB, supernovae, galaxy data, even gamma ray data, all relevant constants and constraints, plus complex but thorough fitting and cross-checks that render nearly no chance for errors, okay? And what you're seeing here is just one of 15 plots showing concordance with the red circle pinpointing the result of the cosmological model. In this plot specifically, it shows dark energy versus dark matter. And dark energy is about 0.7, and matter, which of course is mostly dark matter, is about 0.3 as a fraction of the energy matter content of the universe. The axis is labeled as a fraction of the total energy matter content of the universe. The crossing of many data sets, as you can see, at a single point in this parameter space, which is shown in the red circle, combined data, really tell us this is right. Just look at how much they cross at a single point, right? Nothing funny, right? Not skew, really all across at this sort of the central point, this common intersectional point. In particular, notice the red circle lies right on the line for the flat geometry of the universe, okay? So let me point out, this line points out a possibility, various possibility, but for flat geometry. and the red circle is right on it, okay, saying this is where our universe is, okay. So the result is so strong that it is just incredible. And remember, this is just one of the 15 plots. Okay, I'm only showing you one, and that's enough. And by the way, this is from a WMAP result around 2008. I use this because that was the first time concordance was firmly established. Since then, we have gotten even better, of course, with Planck data and more subsequent supernova data and more galaxy data even on. Okay, later on, the constraint got even better, and our concordance model got even better, okay? When you think about it, that the universe, such a huge and complex space, can be described in just 6 parameters is stunning, it's amazing. If the model is so complex as to require, say, 20 parameters and more, then the model loses more credibility, because with more parameters, then we can play more fitting games and will have greater uncertainty in each parameter. And so in science, fewer parameters is the stronger result, provided that they fit, okay? So the fact that the huge universe and its long history will come down to just 6 says that the universe is not complicated, as shown by the CMB as well as the overall result of the concordance model. Of course, the processes at various stages have additional complexity, and the specific detail of the interaction by gravity, nuclear forces, and electromagnetic forces are understood to be a part of this model that will continue to operate to make this universe more and more complex. But these are finer details, okay? So here, the concordance model is the big picture model, and the remaining parts are detailed for the complex interactions at various forces at various stages. And let's go through the 6 parameters. The 6 parameters are Hubble constant, dark energy, matter content, both dark matter and the ordinary matter together, and reionization. Reionization is the extent of the impact when galaxies and stars began to form across the universe, thus impacting CMB photons, and how far some can travel before being interfered with it again. The effect will eat up some CMB photons, but it can be calculated and quantified as well, so it's not a problem. And then there is inflation, as we have discussed, to address issues such as flat geometry and isotropy of the universe. We do need to put that in. And finally, we must believe in quantum physics and put in as a necessary condition the magnitude of the vacuum fluctuation that gave rise to anisotropies in the universe as observed in the imprints of CMB. Of course, both inflation and quantum fluctuation remain kind of on the abstract side, but it is a necessary part of this model, and we can make it work. That's why it's very credible. It's just amazing that we can talk about inflation and quantum fluctuation at this level, okay? And so what do we know? We live in a quantum mechanical, dark, evolving, and runaway universe, okay? If you think about this statement is completely the opposite of what people believed in even 200 years ago, okay? The world didn't understand quantum physics. The world certainly did not think the universe was dark. The world certainly did not think the universe was evolving, and certainly no idea that it's running away. So everything we know today is going completely the other way. Isn't that amazing? All right. And there's, of course, so much more, such as consistency with 3 generations of particle in particle physics. And there's also particle desert, okay, the mysterious lack of additional particle beyond the standard particle physics up to a very high energy range that we have probed. And that is quite a mystery. But our cosmological model is fully consistent with particle desert, meaning what we know now is true, okay? Meaning that there is indeed no particle after the standard model as far as we know. And that is a problem for theorists as well. Well, so what more can we do? Well, currently for the astronomers, Hubble tension is probably the most prominent issue. Different astronomical observations result in slightly different Hubble constant, ranging from 65 to 74. And yet with more and better measurements, this tension has not improved, and in fact got a little bit worse. And that's a puzzle. CMB result itself gives a Hubble value on the lower side at about 68. And so far, we do not know why, but this issue must be resolved because this is a Hubble constant is a huge issue in astronomy and cosmology. It is the big prize, okay? And we do not have any reliable physical model for dark matter and dark energy. And we certainly do not have any formulation of quantum gravity. I mean, people try, and there are good ones, but we cannot show them or prove them to be, the correct one. And so we don't have any viable model or way to describe early universe in the Planck regime, okay, appropriate for that time, okay? But in terms of technology and observations, we are really humming along. James Webb is going to see more galaxy, and earliest one too. As I stated, James Webb is particularly designed and suited to be able to pierce all the way back to see the first light, okay? Now, I was not sure long ago if that can really be successful because 400 million years after the Big Bang is so long ago and so far away. But amazingly, again, we did it. It is looking like, we can do it, and we are doing it with some observation already made. So great, okay? And this is why you want to take this course, to have someone who knows telling you that this is one of the main purposes of James Webb, and that it is designed to be able to achieve this cosmological result, okay? As far as I know, no public article mentioned this, but astronomy community, okay, we know this, okay? This is pretty standard information. Now, I also mentioned Vera C. Rubin Observatory, formerly LSST, designed to do quick and continual sweep all sky surveys from the ground, doing deep, going wide, and going fast. But it's not yet surveying as of mid-2026, but it seems to be already ready for prime time. And I'm waiting for Vera C. Rubin to begin operation, okay? Also, in terms of a CMB survey, the fourth generation of CMB all-sky survey is likely to incorporate the measurements of polarization signature. Planck surveyor, actually the previous generation, Kobe, WMAP, and Planck, measure the photon energy but not polarization. If you do not know, just know that light or photons can be polarized. CMB interactions with matter in the early universe due to electromagnetic or optical properties will result in polarization signatures, okay? The polarization survey will contain even more critical information and possibly some surprise may emerge, okay? So we have taken the first three generations pretty far and achieved incredible precision. And I think this, as far as we can go, we can certainly do better, but it's marginal gain. So we must well go with the next big prize, and that is CMB polarization. It is just something different. Finally, I want to mention that as of now, there are huge water tanks deep underground to detect neutrinos. I mentioned Kamiokande in chapter 6. Now Super Kamiokande, that is in Japan. There's also Ice Cube in South Pole. And there is a new one called KM3 NET ARC. I don't even know how to pronounce it. To be built in Italy that goes down 3.5 kilometers underground. Wow, that's pretty deep, okay? Now, these facilities, they look like future doomsday bunkers that you see in science fiction movies, but they are real for science, and they are going to seek the path to detect cosmic neutrinos, all right? Now, this won't be an easy task at all, because I really doubt that these things can map out enough to sort of map out the cosmic map, right? The all-sky map of cosmic neutrinos from the background from the early universe, right? From the Big Bang. But we have to try, right? So this may be the first generation, and then maybe 20 years, 30 years later on, we will have third generation, fourth generation. Eventually, we can properly map out an all-sky cosmic neutrino background, okay? But certainly, it's much more difficult than the cosmic microwave background, okay? I've also been paying attention to the theoretical front, and I've seen a constant publication of ideas on simulation universe or the multiverse. I have already mentioned a few words on them, but these ideas are looking increasingly, the way I would say it, less crazy. They are still fantastical, but as people are studying more and more these theories from the established theories that we know, they are looking more and more sound, okay? It's still fantastical, but mathematically, it's not crazy. Now, to finish up this course, I want to remind you where civilization was centuries ago, even millennia ago. We wondered about our universe, only to come to know a much bigger universe in a subsequent stage of discovery. We have gone from Ptolemy's universe to Copernicus' universe, to a bigger Herschel Island universe, and then Hubble's many galaxies universe. The understanding and the definition of the universe have definitely evolved and expanded. The current paradigm shift, including the acceleration of the universe, is ongoing and is not complete because we have not come to know what the next stage is. We are still in the dark, and therefore it is not complete. So now, think about this. We are also in the dark in exactly the same way, okay? Exactly the same way as the previous generation, okay? Including, say, Ptolemy, not knowing the extent of the universe, okay? Especially with this multiverse idea rising strong. Could it be that we are in one of many parallel universes? Okay, well, that's a crazy idea. But if we're going to think of a bigger extent to this universe, if there is a bigger extent, and why should we think that we, whatever we see is the universe, right? Because every generation something happens. Well, if that's the case, wouldn't the multiverse be a reasonable candidate of this expansion idea, okay? With this expansion of our view to a bigger universe. And remember, we discussed that ancient folks were doing funny things like astrology, building geometrical models to understand the universe. Well, we are actually doing similar kind of things, all right? We are really not doing that much different, sort of not exactly blind guessing, but trying to figure out the best we can from the mathematics, the principle we know, try to just build some almost like a Legos model or something like that, just far more sophisticated, okay? So maybe the next getting bigger paradigm shift is the multiverse, maybe, okay? But in any case, I feel we are in the dark of the next expansion of the universe idea. What would it be? We do not know, okay? And I hope I will know something before I die, okay? And okay, so let's take one more look. And we have come to the end of this course. Thank you for participating, and I hope you have gained some amazing insights into this universe. wild beyond imagination. I still cannot get over how many crazy events I've witnessed in my short lifetime. And I do hope you continue to learn about it long after this course ends. Okay?